A very good morning, good afternoon and good evening to all my friends and the candidates and the participants for this course which is under NPTEL MOOC, and the title of the course is Application of Forecasting Regression and Time Series Models. And my good name is Raghunandan Sengupta from the IME department at IIT Kanpur. So, as you all know, even though I am repeating, please excuse me for that. There are three broad areas which we plan to cover in this course and which has been given in the syllabus. The first one is averaging techniques and forecasting methods, second one is regression models, and third one is time series models. So, we are discussing the concept of averaging techniques and forecasting. This is basically the 15th lecture which is in the third week and last lecture in the third week. What is the coverage in this course? Is basically we will continue discussing the example of exponential smoothing with non-adaptive single parameter, and if type permits we will consider another simple example and with a very specific intention for why we are solving that problem. What we have been doing in the fourth lecture, if you remember, we have been going step by step in the solution methodologies for the single adaptive exponential smoothing method. We took a data and we were solving in Excel sheet. The reason being utilizing Excel sheet is would be available to almost all of you. Whether you want to use R or Python codes or MATLAB codes, I leave that to you, but I wanted to keep it as simple as possible. Now, if you remember the model, we will continue and there are certain changes which were detected. Placement of the cell was an issue. So, I have corrected it, and so please pay attention to this problem. I have solved it in different ways. When I tell about the ways, it means actually it is basically considering different parameters, and if you remember the parameters were alpha and beta. So, placement of the alpha was an issue in the last problem, which I said I will rectify, which I have done. So, that will be clarified in this 15th lecture. So, if you see in the slide, you have again as per the data given, which you have seen in the last class. You have the month starting from January to December. In the second column, which is YT, as per the nomenclature is basically the actual value, and in the third, fourth, fifth, sixth, seventh and eighth are the corresponding values for FT, which is the forecasted value, error, which is the difference between the actual value and the forecasted value. Then AT and MT, as you know, AT and MT are the smoothed error and the mod of that smoothed error. And why I am saying mod? Because there was a formula in which in the case of MT you are taking beta into the mod of the corresponding error. Alpha t is basically the parameter which will change, that is why it is the model is named as adaptive single parameter model, and beta is the weight which you are going to give when you want to find out AT and MT. Now, as per the norm, again repeating, F2, which is for February, would basically be considered as Y1. So, that means Y1 is the best predictor for F2, and with this I will go back to the slide and the Excel sheet one after the other. So, this is the slide and the data which you see. So, this is the corrected one. So, let me go back to the Excel sheet. The value we are taking is 0.2 and 0.3, 0.2 for alpha and 0.3 for beta. So, let us consider this. So, you have, as already mentioned, month, Y, T, F T, E T, A T, M T, alpha T and beta. Here alpha T is the starting value is basically taken as 0.2 for month of February and beta is fixed with 0.3. So, as per the formula, we basically consider first is ET, which is the difference between the corresponding value of column B, which has Y, and column C, which has F. So, it is 135 minus 200 is minus 65. Then I come to find out AT. AT is basically given by beta into ET. Beta is fixed, plus 1 minus beta into AT minus 1. So, that is why AT minus 1 is E2 cell value. And also if you remember, which I had mentioned, again I am mentioning that the value of the starting value of A and M are taken as 0, as marked in dark blue color, both in the slide as well as in the Excel sheet. You all know the PPT slides will be shared, and considering that I am going step by step solving the problem, the Excel sheets would also be shared. Why I am saying Excel sheets? Because there will be more than one depending on the type of problem I am trying to solve. So, for point 2 and point 3, you have these values. So, I will take 195, 187, 8, minus 11.25, 16.05, 0.7. This is for April. And MT is basically found out, if you remember, is beta into ET absolute value plus 1 minus beta into M, the previous value, MT minus 1. And alpha was the starting value. Now, in the next cell, which is in G4, the alpha value will be calculated, which is given as the mod of the ratio of AT by MT. That value comes out to be 0.7. So, I continue copying this formula, which is ET, AT, MT and alpha T done from March, and as usual the forecasted value is given by the formula, which is alpha into YT plus 1 minus alpha into FT. So, I am standing at T plus 1, I am trying to utilize F and Y for the last value, giving weights as alpha and 1 minus alpha, and this alpha is changing, that is why it is with the suffix alpha T. So, I copy these all these cell values. When the Excel sheet is shared, please check it. And I have these values. If you remember, based on error, I found out the mean absolute error, found out the mean squared error, and found out the standard deviation. This is just a repetition what I did, and I keep changing these values of alpha and beta, and there based on that I prepared the cell. So, consider the values which are here for 0.2 and 0.3 respective values for alpha and beta. The MAE, which is mean absolute error, and standard deviation is basically based on the mean square. The values are 68.271. So, if I see, I will just mark it. I will use the color here, if it is possible. No, it is not. Let me check. I will use a, say for example, red would be fine, because it will be help us to make the difference. So, this value goes here, and the value I will use the green color, the standard error goes here. So, they are 68.271457 and 78.362262. So, when I utilize that, I will erase this, because I do not want too much of coloring to clutter our diagrams. So, in this way, let me remove the green color. Yes, done. So, for value of 0.2 of alpha and 0.3 of beta, I have MAE and standard deviation. So, let me do it for 0.2 alpha and 0.5 of beta, and let me check the calculation which I put in the table. So, it is 67.714869, which is in cell number D14, and that matches with the value which is given in cell number K7. Similarly, standard deviation which is given as 82.334152, which is given in D16, matches with the cell number which is given in K8. Corresponding to that, as I keep changing alpha and beta, I have this table which I had shown in the last class. Now, if you see carefully, for a value of 0.9 of beta, the error is minimum. So, if I consider technically for lower value of alpha and higher value of beta, the error is coming out to be the least, at least in these instances where the problem has been solved. So, for alpha 0.2 and beta 0.8, the corresponding MAE is 59.446015, which is given in cell number K13, and standard deviation which is 71.953368 is given as K14. Now, if you consider all the other values, this is the minimum, as I said, for the instances of the problems which have been plotted, considering alpha changes from 0.2 to 0.4 to 0.6 and beta changes from 0.3 to 0.5 to 0.7 to 0.9. And remember the fact that beta has to be between 0 and 1 and alpha also has to be between 0 and 1, because the weights of alpha plus 1 minus alpha is equal to 1. So, this combination of alpha and beta, if you see, is what has been done here. So, for a value of 0.2 and 0.3 of alpha and beta, these are the values. Pay attention with respect to the Excel sheet and the PPT slide. Next, I have just taken as an instance a value of alpha as 0.2 and beta as 0.9. Again, I find out all the values and pay attention to the error term, which is for column ET. And obviously, A and M can be calculated, alpha can be calculated, and obviously F can be calculated. Similarly, for E, by based on the same formula. Only remember, again I am repeating, A the starting value, M the starting value is 0, and alpha the second value, because you are starting at the first position, alpha 2 is 0.2, which you keep changing, and beta is not changed, it is fixed for any run. Similarly, I have in this slide the different values of F, E, A, M corresponding to alpha 0.6 and 0.3. Now, when I am telling about alpha, this is basically the starting value, but if you notice, the values of alpha under alpha t column keep changing because they are adapting. That is why it is known as adaptive exponential smoothing average. This is the slide corresponding to 0.6 and 0.9 corresponding to values of alpha and beta. Again, pay attention to forecasted error, and correspondingly you can have a look at the error term, the M values, the A values. Now, here what I have drawn is for a combination of alpha 0.2 and beta 0.3. I plot the values of y and f. Y is basically the actual value, f is the predicted value. Y is given in dark blue colored, predicted value is given in red color. So, if you see, there is this difference, and this difference is basically what I mean by the error. So, I will use, say for example, the orange color. So, when I am considering the value for me, this is the error which I have, and that what we were trying to plot in the column given by ET. Similarly, if I consider for October, this is the error. So, to make it more clear, this is the error for May and this is the error for October. I am using different colors for the month, so there is no confusion. Similarly, when I consider a combination of 0.2 and 0.9 corresponding to alpha and beta, again the same nomenclature coloring scheme for Y, which is blue, dark blue, F, which is red. I have the graph, and when I try to find out, this is the error for May, this is the error for October. So, May is here and October is here, again different coloring scheme. So, there is no confusion. Find again we have for 0.6 alpha and 0.3 beta, we have the error which will be noted down very soon, but the graph gives you dark blue for Y and red for F, which is basically respectively the actual value and the forecasted value. Error for May, error for October. This is for May as being noted down. This is for October as being noted down, again different coloring scheme to mark. See, if you look at these values of Y, they are fixed, but F is changing. So, you want to take that value set of values of F using a particular model where you minimize the error, and you will consider that model as the best one in under the realm of adaptive single adaptive exponential smoothing method. There can be other methods also which may give you better results, like moving average can be, then non-adaptive single parameter exponential model can be better, or non-adaptive multi-parameters exponential model can be better. There can be other models also which can be better with respect to the single parameter adaptive model which we are considering now. In this slide, we have again dark blue for Y, red for F, which are corresponding actual and forecasted value, and these are the errors as marked. I am only marking for May and October just for illustration. You can have a look corresponding to the other errors for other months also. This is error for May and this is error for October. Red line is changing, dark blue which is for actual value remains fixed. Now, what I would do is basically the following. The same table we have already seen in the Excel sheet. I have just copied it such that there is a continuity in the discussion. So, for different combinations of alpha and beta, alpha changing from 0.4 to going down to 0.2, going up to 0.6, and beta changing from 0.3 to 0.5, 0.5 to 0.7, 0.7 to 0.9, you have all the values corresponding to the MAE, mean absolute error, and the standard deviation, which basically the square root or the variance, and variance can be found out from the mean squared error. Now, the next table, before I go to the next table, I will switch on to the Excel sheet. So, this is what I will do. I have a graph and I will show it corresponding to the fact this is easily visible to all of the participants. So, I consider the values of alpha, say for example 0.2, and this is alpha 0.2, and what are actually they are calculating are as follows. for different values of beta starting from 0.3 to 0.5, 0.5 to 0.7, 0.7 to 0.9, I find out the different values of the change of alpha. Starting value is 0.2 for all the 4 cases, but that is as they keep changing we have to find it out starting from the month of March to November. So, let us do the calculation and find it out. I will just illustrate one of them. So, if you see the values for March for alpha changes from 0.2 to 0.1446541 when beta is 0.3. Keeping beta as 0.3, these are the values which I have. So, these are the values which I am just marking for the time being. I will not save it, just marking with orange. Then corresponding to beta 0.5, okay, if you want to see the change, I will come to that later. So, 0.2 and 0.3. So, let us go back to this table 0.2 and 0.3. So, I have these values of alpha changing from March to November. I should copy it here. So, these values if you see they are given to 7 places of decimal. Here I am only considering 2 places of decimal. If you expand it you will find out. If you see this value here is 0.70 which is given here. So, the value which I have copied it. So, these are the values 7009346 that I marked in orange only. So, if I go to next value is beta is 0.5, alpha is fixed as 0.2, alpha is fixed which I mentioned. If I copy, so these are the values, and if you see the graph is being generated. What is the graph being generated? I will come to that within few minutes in the PPT slide. Now, when I change it to 0.7 beta alpha fixed, I have the different values of alpha. I copy in this column where on the top is 0.7 as it should be. Finally, for 0.9 for beta alpha being fixed, I have all the values of alpha changing, I copy them and they are given in this column. So, I will mark the first one as beta as, let me change the color. So, it will become easy as light blue. The next one I will mark as orange. The third one I will mark is light gray and the fourth one I will mark as yellow. And why I am doing that? You will soon see. Now, the graph which you see here is basically changing alpha values from February to November corresponding to the fact beta is equal to 0.3, 0.5, 0.7, 0.9. So, if I consider beta 0.3, the blue values which are given in column B which have been marked are plotted in the blue line. Here it is, this blue line which I have just ticked to highlight the points. If I consider for beta is equal to 0.5, the values are here as marked here for beta 0.5. Alpha is fixed, remember, and what you change alpha fixed means starting value of alpha is fixed for all the 4 cases. And the third column which is gray is basically marked for this beta is equal to 0.7 here. And finally, for the yellow one, these are the values again highlighted. Highlight means to make it more specific. Now, the question would be, can I do it for this is alpha 0.2? Yes, because based on that only we have done starting value. So, the question can be, can I keep changing alpha, keep changing beta and generate such graphs? Answer is yes, and this is what we are going to check. Let us go back to the Excel sheet. The Excel sheet shows here starting value of alpha 0.2 and it keeps changing beta As you can see in second column, no, it should be much darker, so it is easy for all of us to see. For second column, for third column, for fourth column, and for fifth column, corresponding to beta 0.3, 0.5, 0.7, 0.9, you have the changing values of alpha. So, for 0.3 of beta, the blue one is the graph which was shown how to calculate in the Excel sheet. For beta 0.5, orange is the graph, as you can see in the right panel in slide. Similarly, for beta 0.7, gray colored graph, dotted graph for all 4 cases, dotted graph, and beta is equal to 0.9, the light orange one. The first one I would say not orange, second one beta 0.5 is not orange one, is basically a dark red. So, I have this graph. So, what does this graph signify? If you notice, there is a fluctuation obviously for all values of beta. So, because the data values, actual values are changing, hence the beta alpha value which adapt itself, adapt in such a sense that you will be able to forecast the values much better than the non-adaptive one, but you have to consider some value of beta for which your metric, which can be either mean absolute error, can be standard deviation, can be U statistic, can be weighted average, whatever, can be minimized to the maximum possible extent. Similarly, in this graph, considering starting value of alpha is 0.4, beta again 0.3, 0.5, 0.7, 0.9, I plot the graphs for the changing values of alpha. Same coloring scheme has been kept, which is blue, dark red, gray and orange, corresponding to 0.3 of beta, 0.5 for beta, 0.7 for beta, 0.9 for beta. Again there is a fluctuation, but interestingly if you see for 0.9 beta the fluctuation is low, and it may not be a coincidence, because if you remember, for a value of alpha as low as possible and beta as high as possible, we are getting the mean absolute error, one metric, and standard deviation as the best for all simulation which we have done. Simulation I won't say, different instances which we have plotted. Similarly, in this table we have for 0.6 corresponding to beta 0.3, 0.5, 0.7, 0.9, again the same coloring scheme for the dotted graphs. Again you see for beta being 0.9, the fluctuation is less, which is more intuitive, because you are getting the best result for 0.9 of beta, and obviously alpha has to be minimized, which we saw that in the table when we highlighted the values of MAE and standard deviation for 0.2 and 0.9 respective values of alpha and beta. With this, I will end this 15th lecture and continue more discussions for forecasting models later on. Thank you very much and have a nice day.